Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
So welcome to MIT Faculty Forum Online. I'm Dan Falk, an MIT Knight Science Journalism Fellow from the class of 2012, and I'll be serving as your moderator this afternoon. Today's broadcast is sponsored in part by the MIT Federal Credit Union, MIT Professional Education, and MIT Sloan Executive Education. As a reminder, we welcome your questions during this chat. Alumni joining us via Zoom can use the Q&A feature found on your toolbar. For those viewing on YouTube, you may add your questions to the comments field next to the stream, and we'll try to get to as many of your questions as we can. If you're tweeting about today's event, you can use the hashtag MITalum. I guess if you're trying to tag me, my Twitter handle is just the same as my name, Dan Falk. Okay, so today we're talking to Shep Doeleman, PhD 95 from MIT. Shep is an astrophysicist at the Harvard Smithsonian Center for Astrophysics, and he is the founding director of the Event Horizon Telescope. If you hear the acronym EHT, that's what that is, Event Horizon Telescope, which is a synchronized global array of radio observatories designed to examine the nature of black holes. Among other awards and recognitions, Shep was named the winner of the 2020 Breakthrough Prize in Physics, and you can read more of Shep's bio in the link provided in the chat. So to get us started this afternoon, Shep has a presentation for us looking at some of his recent work, which I'm pretty sure will include some discussion of black holes and how to photograph black holes. So please welcome Shep Doeleman.
Okay, thank you very much, Dan. I'm going to share my screen and share some slides with you. And first, let me just say that it's an absolute pleasure to talk to the MIT alums. I'm an alumnus. I spent the formative years of my career at the MIT Haystack Observatory, so a big shout out to MIT Haystack. And it was really an honor and a privilege to work with people there. One of my great mentors was Alan Rogers, another Alan Whitney, others, Joe Salat, that's at that facility. And it's been great to work with the whole community there. So MIT is kind of in my blood, love the Infinite Corridor, did my graduate work there. It's a real pleasure to talk to you today about this project called the Event Horizon Telescope, or as I like to say, it's seeing the unseeable and how we capture an image of a black hole. The premise of this visionary project really was to see if we could take a picture of a black hole to see what they really look like, to test Einstein's theories close to the event horizon itself, the one place in the universe where we know that his laws may break down. And more than that, to understand how we might understand how black holes energize the centers of galaxies, how they change the way the night sky looks when we look at the cosmos with our most powerful telescopes. And these results are presented on behalf of the EHT collaboration. So I want to motivate this by showing you an optical picture of the galaxy Hercules A. This is a galaxy that's about 2 billion light years away. At the very center of it, we think there's a black hole that weighs 4 billion times what our sun does. And it looks fairly innocuous when seen in the optical, but when you put radio goggles on, when you look at it in the radio, you see these incredible jets, high-speed jets that are streaming from the center of this galaxy. And to put this in perspective, these jets span 1.5 million light years, and they contain an equivalent energy of about 3 billion supernovae. So the only thing that we know of that can power something like this and direct oppositely propagating jets from the center would be a spinning supermassive black hole. And you see them primarily like this in the radio. And this is what we're going to use with the Event Horizon Telescope to peer deeply into the event horizon of this black hole. Now, what would we see if we could have infinite resolution goggles? Imagine you could be at the black hole itself. What would you see? Well, the light bending is so severe that you wind up seeing what we call the black hole silhouette or shadow. And the 3 panels that you see here are models and simulations that have been done over the years. And they all show some common features. And they show common features because the gravity is so dominant that it basically controls everything that we see. You wind up seeing a dark shadow in the center, and that's where the event horizon is. Light that crosses the event horizon doesn't escape to us because the event horizon is the point where the force of gravity is so strong that light can't escape. So we expect to see this shadow. But beyond that, we see usually a brightening on one side. And that's because the gas circularizes around the black hole at near light speed. So some of it's coming towards us and some of it's going away from us. There's a Doppler boosting effect. So one side is typically much brighter than the other due to the rotation of gas around the black hole. And most of this is seen in the radio. So the black holes that I'm going to talk about today shine brightly in the radio. And those are the photons that can reach us from the event horizon. What's important to note is that when you solve Einstein's equations, you wind up finding the diameter of that shadow to be related by the equation in the bottom right of the screen, the square root of 27 times a handful of constants. And that handful of constants is important, right? That's the Schwarzschild radius, 2gm over c squared, 2 times Newton's gravitational constant times the mass of the black hole divided by the speed of light squared. So what this means is that if we could lay a ruler across space-time, if we could make this image, measure the shadow, we could directly test Einstein's predictions right near that black hole, and we could measure the mass of that black hole in a completely geometric way. So next, I want to show you how the gravity forms this shadow. So around the black hole, there is very, very hot gas, and some of the light rays are bent mildly by the black hole's gravity. These are what we call the n=0 paths, which are just deflected somewhat by the black hole. And you can see there the central depression with a lot of gas illuminating the exterior. And the n=1 photons make about half an orbit around the black hole. These now are lensed very precisely to a much more defined ring around the black hole. And later we get the n=2 paths, which make a full orbit around the black hole. Now these photons illuminate a very razor thin ring. And this really is the ring that we're after. This is defined by the photon orbit. That ring marks the point where photons orbit the black hole multiple times. Anything interior to that, they fall into the event horizon. Anything exterior to that, they escape to our eyes. So you wind up seeing a lot of gas distributed around that photon ring and the photon ring itself, and that's what we're after. So then the question is, and you can see here, this is the dimension that we're after to measure, to lay a ruler across that. Now, what wavelength should we observe these monsters in? And it turns out that you don't want to observe at too long a wavelength, because then the gas itself obscures the event horizon. So you're seeing here an image of what the black hole would look like with jets coming out either side at long wavelengths. But now let's look at higher and higher frequencies. By the time you get to a wavelength of 1 millimeter, then you can see clearly the beginnings of the jet and that circular feature. And now we run forward in time in the simulation by the University of Arizona colleagues, and you see that the black hole is a dynamic place. Gas is really orbiting around that, but it does lens around that last photon orbit to give us that ring. And now what source are we going to look at? Well, there are only 2 sources we know of that are large enough in the sky that have a combination of being close enough to us and a black hole massive enough that we can hope to resolve this event horizon with a telescope on the Earth. I'm going to focus on one today called M87. It's in the Virgo cluster. And you can see here a Hubble Space Telescope image of it, and you can make out an optical jet. This is a jet coming from the center of the galaxy that we see in the optical. And this is about the bar in the lower right shows that we're looking at features about thousands of light years across. Now let's zoom in on that optical jet and overlay the radio jet on top of it. And there's almost a 1-to-1 correspondence. The radio jet lies directly on top of that. So now we're looking in the radio, and you can see the jet off to the right, but there's a ghostly image to the left. Now, what is that? It turns out that this is a 2-sided jet. the black hole is launching light speed jets from the north and south pole. We see the one coming towards us because of that Doppler effect. The jet going up to the right is pointed almost directly at us, only off by about 17 to 20 degrees from our line of sight. The jet going to the lower left is pointed away from us, so it's Doppler deboosted, very faint, we don't see it, but they're really two jets. Now let's zoom in. So we start here, and with other telescopes, we can get to 1,000 light years across, and we still see that jet. And now we're 12 light years across, zooming in by orders of magnitude. And then some of the best images we have now get to 4 light years, but always we see this self-similar jet going towards the core at the lower left where we think the black hole lives. And then this is the best image that we have to date, about 1/3 of a light year across. And we still don't know, as of just a couple of years ago, we didn't know what was inside that core, what was driving this relativistic jet in the galaxy M87. And the idea of the Event Horizon Telescope was to zoom in on that inset to see if at a high enough frequency we could see all the way to the event horizon, and with a sufficiently high fidelity telescope we could image the black hole itself. Now the problem is that if you want to photograph a black hole shadow, you need a couple of things. The basic formula for the angular resolution, or the smallest size a telescope can see on the sky, is the wavelength of light at which you're observing divided by the size of the telescope. So you simultaneously want small wavelengths, short wavelengths, and a very, very large telescope. Now, let me put this in perspective. The shadow size for M87 is 50 micro arc seconds across. That is the same as trying to see an orange on the moon, or holding an atom or molecule at arm's length and being able to see it. So it goes beyond any conventional telescope's capability that we know of. Now, as I said, we need to see through that hot gas around the black hole. And so we want to go towards about 1 millimeter wavelength, which allows us, or 230 gigahertz if you prefer frequency, which allows us to see all the way to the event horizon. We also have to be able to look through the interstellar gas between us and this black hole. And when the photons finally make it all the way to Earth, they have to make it through the Earth's atmosphere to our telescopes. It turns out that 1 millimeter wavelength fits all of those criterion. It comes from deep in the gravitational well, through the interstellar medium, through the Earth's atmosphere, and they can be collected by radio telescopes on the Earth. The only problem is that if you look at that boxed equation and you put 1 millimeter in there for the wavelength, the telescope size would have to be 10,000 kilometers. So how are we going to build a telescope that is 10,000 kilometers across? And we do something called short wavelength, very long baseline interferometry, a technique that really had its origins partially at the MIT Haystack Observatory, where I did my postgraduate work and worked for many years. And the idea here is that you collect data at telescopes separated by thousands of kilometers on the surface of the Earth. And you time tag the data that you receive there from the black hole with atomic clocks that lose about 1 second every 10 million years. So they're very, very stable. We record the data on hard disk drives, and then we ship them to a central processing facility. And there's one of these at the MIT Haystack Observatory, and also one in Bonn, Germany that we use. So in effect, we are freezing the light and then combining it later in silicon to mimic what an optical mirror does for a more conventional telescope that we could look through with our eyes. And just as the shape of the telescope that we see in the optical is a nice parabola, and light rays bounce off the surface of that parabola and come to a focus at exactly the same time where we can put our camera, we can adjust in our electronics the delays between these telescopes to form an interferometer as large as the space between the telescopes that are participating. So each pair of telescopes on the ground effectively gives us one data point, one silvered bit in a virtual Earth-sized telescope. So we, of course, wanted to build out the array and add as many telescopes as we could. So we have the SMT in Arizona, the Large Millimeter Telescope in Mexico, the submillimeter array and the James Clerk Maxwell Telescope in Hawaii, the OPEX telescope in the high desert of Chile, the ALMA telescope there as well, We have a telescope at the South Pole, and our European colleagues bring in the IRAM telescope in southern Spain. But even this is not enough. Even having these dishes only gives us a few silvered points in this Earth-sized virtual telescope. And thankfully, the Earth rotates. And that's really the secret here. So on the right, what you're seeing is the assembly of this Earth-sized virtual aperture. And on the left, you see all the pairs of telescopes linked by these red lines that form the dots that are circulating in the right. So during a night of observing, we take a few silvered points on this virtual telescope and turn them into a web. And we get enough points, we're able to reconstruct the image. Now, for those who remember Fourier analysis, each interferometer pair, each telescope's pair is sensitive to one Fourier component of the image brightness on the sky. So you can look at that, you can say to yourself, any brightness distribution on the sky, any image of the black hole can be decomposed into sines and cosines. And each of these telescope pairs is sensitive to one of those components. And when you get enough of them, then you can recreate the image. Now, I'm not going to bury the lead. This is what we wound up seeing, and I'm going to tell you a little bit about how we saw that. But this image just, it's such a clear confirmation of Einstein's theories, the predictions that were made nearly 100 years ago of what the impact parameter of a black hole like this would be, were confirmed with startling clarity. You see the ring. This is the last orbit of photons around the black hole. Inside of that ring, there must be 6.5 billion suns. That's the mass of this black hole. So we have tightened the noose around this black hole by many orders of magnitude. There's no wiggle room now. This really has to be a black hole. And beyond that, you can see the expected asymmetry. So we see a faint region on the top, a bright region on the bottom. That's exactly what we expect from light speed gas hurtling around the black hole. So in the bottom, it's coming towards us. On the top, it's moving away from us. And that allows us for the first time to understand and to measure the spin axis of this black hole. It must be pointing slightly into the page. And take your right hand, do the right hand rule. My thumb is going into the page, and then the fingers circulate around towards you from the bottom. And that explains why the bright part is at the bottom of the page. And more than this does really confirm all of the theories that we hold dear about Einstein and whether they really work at the boundary of the black hole. Now, a little bit more about how we made this image, because it's important to understand that even though we have many baselines, even though we have many telescope pairs, we don't have enough to reproduce a full image. So we have to model, and we have to use maximum likelihood methods to create that image. So the first thing we did was we split ourselves up into 4 different teams because we wanted to remove the human bias out of this process. So we had 4 teams largely separated by geographical region, but also by the techniques they were using. And the reason that we do this is that we really want to involve many, many people. So we have, I'm just overjoyed to be able to share with you all of these images of people that were on the teams, team 1, team 2, team 3, and team 4. And this was just even a small part of the entire Event Horizon Telescope collaboration. So one of the nice things about directing is that you get to work with amazing people from all over the world. And the other reason that we split up is, as I like to say, because labradoodles do look a lot like fried chicken. And it's very easy to fool yourself into thinking that you're looking at a piece of fried chicken when it's actually a labradoodle. So we wanted to avoid any group think here. We wanted to have 4 separate teams looking at the data completely independently. And if you think that's hard, chihuahuas and blueberry muffins are an entirely new level of complexity. So enough of that. The important thing is that when these 4 teams applied their different techniques to reconstruct these images, they came up with 4 very similar looking distributions. On the left, you see regularized maximum likelihood techniques, which do a chi-squared fitting, but have regularizers which steer the process. So they say, for example, the distribution has to be smoothly varying. It can't be stippled. but that's a very reasonable kind of constraint to use. And on the right, we used a more traditional clean method, which deconvolves the image in a series of iterative steps. But no matter how we did it, we got the same basic structure. And here we are celebrating in the basement of the Black Hole Initiative at Harvard. This is only a fraction of the people that were involved. Many more people on a speakerphone celebrating this first result with us. And the next thing we did was, as good scientists, we tried to make this result go away. We did everything we could to remove this ring from our results. And we did this by training our algorithms on different kinds of shapes. So the two on the left, we trained our algorithms on uniform rings, on crescents, but we also trained them on filled disks, and we also trained them on doubles. And when we had these algorithms trained perfectly on these other kinds of shapes, then we set them loose on the M87 data anew. And even though they had been trained to produce doubles or filled disks, these were the results we got at the end of the day. So 3 different methods here produced 3 virtually identical black hole shadow images. This gave us great confidence. What also gave us confidence was the fact that we had observed this black hole on 4 separate days. Each day, each data set completely independent of the next gave us the same black hole image. And on the bottom, you see the collection of all the Fourier components, the virtual aperture I showed you before filled in as it was for each of these days. Now, of course, with very long baseline interferometry, it's all about location. So I wanted to show you the power of adding more sites to the ultimate fidelity of the image. When you have just a couple of sites, all you can really tell is the size of the image on the right. When you add a more distant site in Chile, to the ones you saw there in Mexico and Arizona, then you get more angular resolution, but you can't tell what the underlying distribution is. As you add more, the ring shape slowly forms. And when you get the full spanned distance across the globe, that's when you get the highest imaging fidelity. And then the same thing happens with Earth rotation. You can see here that as the Earth rotates in the center, in the upper part, we fill in that virtual lens. On the right, you see data. And then on the bottom, you see the 3 different methods and the best image you can make with the cumulative data up to that point. And you can see that as the Earth rotates, the imaging fidelity greatly increases. And you wind up seeing telltale signatures in the data all the way to the right, which I can explain a little bit later, which show that we're seeing a ring and not a filled disk. It's the dips in those data. I'm not sure if you can see my cursor, but it's the dip here that comes down and the other dip here, which shows you just in this data plot that we're seeing a ring and not a filled disk or a double. And then we can make precision measurements at horizon scales from this. So here, this is a method that we devised, is shown by one of our postdocs, Dom Pesci, where you measure the size of that ring all the way around, and you look at the radius, the distribution, and from this we wind up getting the size of this shadow. And using that size, for the first time, we can measure directly the mass of this black hole. So remember, we're measuring an angular size on the sky. So it's only by knowing the distance to M87, which is 55 million light years, combined with the angular size we get, which gives us the linear distance across that ring, which is about 3 solar systems. And that tells us the mass, which is 6.5 billion times the mass of our sun. And that agrees with other mass estimates of that we get through velocity of stars moving around the black hole at much larger distances. So everything begins to agree. And this gives us great confidence, of course, that Einstein's theories are correct at the event horizon. Now, where are we going next? That's the question I always get. We want to build out something called the next generation EHT. Up to this point, we had to go where the sites already existed, where radio telescopes already were. And now we want to add many more sites shown here in blue that will fill out the virtual lens and give us much better imaging fidelity. As an example, you see here on the left, the jet of M87 and the black hole. And currently we can only make an image of the black hole, as you see here in the inset, because we don't have the sensitivity to image the low surface brightness emission from the jet as it's just beginning to emerge from the black hole. In the middle is what we can do with the array that we fielded in 2017. We can tell there's some emission around the black hole, but we can't show exactly what the structure is as the jet is launched. But with the next generation EHT all the way to the right, when we build this out and double the number of dishes, we'll be able to do that in exquisite detail, forging this important connection between the jet and the black hole, answering that question, how do black holes launch these jets? And then we don't want to be bound by the surface of the Earth. Who does? On the left, you see, again, that rotating Earth and filling in the Earth-sized virtual telescope. And on the right, you see what can happen when you have 4 space telescopes in low Earth orbit. It's remarkable. You wind up filling the Earth-sized virtual telescope in almost perfectly in just one evening. So that will allow us to make real-time movies of black holes. And that's what I'm going to show you next. Imagine black hole cinema. This is really where we're going in the next decade. 10 years ago, we promised that we would make an image of a black hole. And now we feel very comfortable saying that we are hoping to make the first movies of black holes by the end of the next decade. On the left, you see the model. On the middle, you see what we can do with a low Earth orbiting satellite. On the right, you see what we can do with also a geostationary satellite. And this is a global effort. We started this 20 years ago with a very small group of people. Really began at MIT and Haystack Observatory, where I formed a group to do this. And now we have a 200-member collaboration, 60 institutes, 20 countries and regions. This is only about half of us at a meeting in Hilo, Hawaii. If you want to build a global telescope, you really need a global team. And it's been the pleasure and honor and privilege of my career to work with all of these people. And the impact has been quite astounding. It really knocked us back a bit on our heels to see, when we came down from our hotels the day after the announcement, this black hole image on the front page of every major newspaper around the globe. It really speaks to people in a way that we hadn't quite predicted. It was a group of people working together across borders, tackling what seemed like an impossible challenge and not giving up and succeeding. And I would venture to say that in these days when we are facing real global problems, especially hunkered down in our houses now in the face of this virus, that this EHT effort gives me hope that we can harness the collective resources and intellectual power of experts around the globe to tackle problems like that, not to mention climate change and others. So with that, I'll end, and I'd love to take any questions that you have. This has been very inspiring to us, and we hope it inspires you too. Thanks, Dan.
Thank you, Shep. That was terrific. Hopefully everyone can hear me. I am not muted, so you folks should be able to hear me. I'll get the ball rolling. I see a number of questions have come in on the Q&A thread. I'll just get the ball rolling by asking a couple of things. And yeah, I mean, what a stunning achievement, and international in its nature, and really just remarkable in so many ways. This, of course, was M87. Do we expect that? I mean, do we think that that black hole is typical? Would other black holes in our galaxy? I mean, do we? I guess they might be oriented differently. So I assume that's something that would differ. But I don't know. Do we think that one was typical?
Well, so the galaxy in M87, the black hole there, is pretty typical because it's what we call a low luminosity active galactic nucleus. So it's actually fairly low energy, and it's fairly nearby, and we think it's typical of most of the black holes that would be around. The other target for us is Sagittarius A star in the center of the Milky Way. And that source is, of course, much closer because it's in our own galaxy, but it's also about 1,000 times less massive. So it appears to be about the same size on the sky. Those are the only two sources that we know of at the moment for which we could resolve the event horizons. But of course, if we were to launch a telescope all the way out to the second Lagrange point, for example, 1,000,000 kilometers away, then we would be able to resolve many, many black holes across cosmic time.
And you mentioned the black hole at the center of our galaxy. So is that on your hit list? Is that something you can have a look at?
Hit list, that's kind of a loaded term. Maybe a wish list.
Wish list, yes.
Yeah. So we do have data on that, and we're working actively on that black hole. That's called Sagittarius A star. It weighs about 4 million times what our sun does. The problem with that, or the challenge, the opportunity with that black hole is that because it's so much smaller, it evolves 1,000 times more quickly. So
Mm,
during one evening, the M87 black hole remains motionless, and we can use all the data we collect during a night to make an image. For
mm,
Sagittarius A star, it changes moment to moment. So it's as though you're taking the lens cap off of your camera while you're trying to take a picture. It gets very blurred. So we really have to think about making video to really understand what Sagittarius A star looks like. So it's taking us a little bit longer, but I'm confident that we'll develop the algorithms to do that.
mm. One more thing I couldn't help thinking of as we were looking at those images, and of course they're very spectacular. Now those are radio wavelength images, but if you could get up close in a spaceship, and I appreciate that this might not be something you want to do necessarily, but if you could get up close to one of these, what would it look like in the visual? What would a human being actually see if they got to an equivalent position where it took up this part of the sky like that?
Yeah, that's a very good question. So the images I've shown are for a screen that is basically at infinity. When you get very, very up close, you're going to see, you might wind up seeing much more of the distortion of the background. So you might see stars and hot gas glowing in the optical around being lensed around you. And of course, as you got much closer, then everything starts to be lensed the closer you get. So it would be a little bit different than you see here, than the images that I've shown you. Again, I don't think you'd want to get that close. We're hoping to do a lot of remote monitoring of this black hole. But yeah, I'd have to think about that a little bit more. There have been animations done of people falling into black holes, and they take into account the full light bending at these very
Right.
short distances between you and the black hole.
Right. That's fascinating. Well, we have a number of questions from our audience, our virtual audience. A few, some of them are more technical than others, but someone asked about what drives the jets. What is the role of plasma in the creation of a path between objects?
Oh, that's a great question. So what happens is that as the gas moves towards the black hole, it's totally ionized. So it sweeps up magnetic fields as it approaches the event horizon. So the magnetic fields get stronger and stronger. And then it's the relativistic motion of electrons around those magnetic fields that release synchrotron emission. And that's what we see in the radio. But these magnetic field lines are then forced to rotate with the black hole. They're frame dragged with the black hole. And so you get this egg beater motion. And those same relativistic particles that are orbiting around the magnetic fields as a bead in a wire are then flung out at relativistic speeds by the spin of the black hole. That's what drives a jet from the North Pole and the South Pole. They're basically magnetically driven, and it's the plasma that is flowing along those magnetic field lines.
Okay, that's interesting. Does that make it, because I know we have jets associated with things like what, neutron stars and pulsars. Is this a related phenomenon?
You can get the same kind of thing around other objects. The most energetic ones, though, are around black holes like this.
Okay. And we have someone asking, was it a coincidence that the image appears to view the black hole head on? He says, I would have expected our view to be at some angle to the accretion disk around the black hole, not perpendicular. So is that just a matter of luck? Is it a geometrical luck, so to speak?
Yeah, a little bit. So it turns out that many of the black holes that we see because they are beamed towards us. So it's the idea that when you have black holes that are oriented such that you have a jet on either side, you might have the center not as bright because it's not coming towards us. It's not Doppler beam towards us. So there's probably a slight selection effect there. But for Sagittarius A star, we have no reason to believe that that is oriented towards us. We haven't even seen a jet from that source yet. So it could be that the jet is really not important to what we see.
Well, that's interesting. So, I mean, does that mean that Sagittarius A star might be almost impossible to get a good photograph of if it's just angled the wrong way?
Well, no, there's kind of a balance. So around the black hole, you get this accreting flow, which is tens of billions of degrees. So it's extremely hot. So it's glowing. But you also get these jets emerging. And the balance of where the photons are coming from, are they coming from this disk of material, or it's kind of a large accretion flow of material, or are they coming from these nascent jets emerging from the North and South Pole? It turns out when you do the modeling, there's an admixture. Some of them come from the jet, some of them come from the disk. It depends on exactly what models you use. What we do understand is that the space-time is so deformed around the black hole that that really determines what you see. It doesn't matter whether the light is coming from the disk or the jet. You still wind up seeing this photon orbit. So whatever is lighting up the space-time, we should be able to see it. And for Sagittarius star, it may come more from the accretion flow and not from the jets. Of course, we don't see big jets coming out of our galaxy, but we would still see this feature and be able to test Einstein's predictions.
I'm seeing a lot of questions here, so apologies to not, I obviously won't be able to get through every single one of these, but I'm just skimming through here for a second.
Dan, I've got all day.
Oh, okay. Well, all right. I guess I don't think I'm going anywhere either. Let's see.
I saw one question that I'll answer while you're
please.
looking.
Yeah.
I saw one, someone said, why don't you put a telescope on the moon? And what a great idea. We've been thinking about putting a telescope on the moon or at the Lagrange point. The problem is when you have a telescope too far away, then you can over-resolve the black hole. But what we're beginning to understand now through that video that I showed at the very beginning is that some of the photons form a razor-thin ring at the photon orbit. So it could be that a telescope on the moon would be able to resolve just that purely geometric feature around Sagittarius A star and M87, and also start to bring into range the event horizons of even more distant black holes. So we used to think that the moon might not be a good place to put a telescope because it would over-resolve it. And now we're rethinking that. So this is just one of the ways in which this new image has caused us to come at things from a different angle and reassess. So it could be that the moon would be a very, very interesting place to put a telescope.
Oh, that's very interesting. Yeah, I didn't even know over resolution was a thing. So that's very interesting. Okay, someone is asking, what can X-ray observatories in space, such as Athena, future mission of ESA and JAXA, what might an X-ray observatory like that contribute to these studies?
Yeah, very, very wonderful question. So more and more, we're thinking about this from a multi-messenger standpoint. So we can see the event horizon and start to resolve it, but all the material around the event horizon emits also strongly in other wave bands, X-rays, for example. So we know that Sagittarius A star and M87 emit strongly in the X-rays. And there we want to do energetic studies, do time-based studies, and understand the flaring structure of these black holes. So every once in a while, both M87 and Sagittarius star erupt with these flares. And we'd like to understand what causes those flares, what turbulence in the flow, what change in the accretion structure forms these impulsive events. And we can observe them in energy and time with the X-ray satellite, which gives us a wealth of information. But if we can combine that with the EHT, then we can describe spatially what's happening at the same time. So more and more, I think it's the union of these different wavelength facilities, which will really start telling us more about how these objects evolve.
Very cool. Yeah, and if you happen to see a question that catches your attention, Shep, that's cool. I'm just scrolling through to find.
Yeah. Well, there's one person here asks, over the course of the Earth's rotation, how many data pairs are you able to get? So it turns out that it's kind of the simple combinatorics. It's n times n minus 1 over 2. So with 6 sites, you wind up getting 15 different points. And then of course you rotate. So then you have to ask yourself, how long do you have to integrate before you get a detection? And that would form one instant of time, and then you'd move with the Earth, get another instant. So you wind up getting 15 times the number of integrations that you can get. But you could wind up with hundreds of points. But we also have to integrate sometimes to get the signal to noise. So I would say that roughly we have about a small handful of hundreds of data points.
Somebody was wondering if there's any upper limit to the size of black holes. At least I think that's what they were getting at. So I don't know, is there an upper limit? Can these things just
Wow,
keep
what a wonderful question. We do not know at this point what the true method of the growth of black holes is. Like, how do they achieve these sizes? If you were to look at the accretion rates, the rate at which these black holes eat now, then they would have to eat at that rate for much longer than the age of the universe in order to reach their current size. So there has to be some other mechanism, maybe hierarchical merging or periods of great feeding that happen earlier in the universe. But even so, the largest black holes that we know of that we've modeled are about 20 billion solar masses. Now, there's no reason why we couldn't have something larger than that. Those are just the largest that we've seen so far. Our wish is that one of these will start to be bright in the radio. We'll start accreting enough and will emit enough radio emission that we can view one of those with the EHT. And then we'd be able to look at black holes that are even larger than M87.
And regarding the ones, so the ones that are in our, we've already talked about Sagittarius A star, but I suppose our galaxy is full of smaller black holes that are just a few solar masses big. Is that the thinking?
Yes. So there are two varieties of black holes. One is of the supermassive variety that occurs only in the center of galaxies. Maybe there's one, maximum two in every galaxy. But of course, black holes are born in supernovae explosions, right? So we expect there to be many billions of black holes in our galaxy. And I think I have that right, billions. The problem is that they're just too small. There's no way that we could ever resolve them with the kind of techniques we're talking about here. Even with space techniques, they would just be too small.
But that by itself is kind of fascinating, that we're getting our best look at a black hole from a black hole that's not even in our galaxy. Like, it's just really, really far away, instead of these so-called neighborhood, I just made that term up, but our neighborhood black holes that you'd think would be easier to get a look at. So that's kind of interesting.
Yeah. I mean, yeah, we can't have a beer with the M87, but we do feel it is close enough by.
Yeah. All right, let's see here.
Now, I would also add that for stellar mass black holes, the LIGO detection, which was also led at MIT and Caltech, and famously by Ray Weiss, who was actually TA'd for Ray Weiss at MIT. So it's and I talk with him about this occasionally. But he and his colleagues really made the discovery of merging stellar mass black holes through LIGO, and you can hear black holes merge through the ringing of space-time and gravitational waves. Those are down at the several tens of solar mass scale. We're seeing Einstein's theories confirmed visually at the billion solar mass scale. So over a dynamic range of about 10 to the 9th, we're seeing Einstein's theories hold around black holes, which is in itself very comforting.
Yeah, and I know we don't have time to get too far into like the history, but it's been 100 years, give or take, since between the idea that these objects might exist and the work that you've done and the work that the LIGO people have done to actually get the data and say, yeah, this is what they're doing. I mean, that's just amazing that that a whole century went by from prediction to confirmation.
Yeah, I really view this as a continuum. I mean, it's rare in intellectual pursuit or in our everyday lives that we're able to make a strong connection with things that happened 100 years ago. But we really do feel a strong connection to Einstein, to Schwarzschild, to the pioneers who started this. And more than that, when I think that COVID-19 has me down and that I'm cooped up in my house and I'm being slightly less inefficient than I usually am at my office, I think of the fact that Schwarzschild solved Einstein's equations in the trenches of World War I. And then I kind of think I don't have it so bad. But there is this connection and confirmation and we're part of a larger story, which is very motivating for us. I see another question here. Haystack was used for computer analysis, but was the big Haystack radio telescope used at all in the EHT? So of course, Haystack houses one of these correlators, which is a supercomputer, which combines the data to produce a data set. That data set is later, used for imaging. It turns out that the Haystack telescope has not been used for the EHT yet, but it may be used in the future. It's large enough, its surface is smooth enough that we may be able to use it going forward. But then again, it's also at sea level. And one of the big problems for radio telescopes is water vapor. At the frequencies that we're observing, it's the water vapor that's the primary culprit that absorbs the radio waves. So typically we want to go to mountaintops at 10,000 feet, 15,000 feet. So it would be a struggle to use Haystack simply because of the weather, but there may be some times during the cold winter when it could be used.
Okay, so somebody is asking, why is gravity wave propagation limited to the speed of light? This is, I guess, stuff that you didn't tackle head on in your talk, but it's still interesting stuff. Why is gravity wave propagation limited to the speed of light? Just after the Big Bang, space expanded much faster than the speed of light, and gravity waves are expansions and contractions of space.
Okay, yeah, well, I'll say I'm not an expert on gravitational waves, but the Einstein equations, they do have a solution for gravitational waves, and they do propagate at the speed of light. The information propagation, or the fact that one point in space can know about another point in space during this expansion, this inflation you're talking about, that's a different concept. And I don't think that information transfer is violated there either. But the gravitational waves themselves are always traveling at the speed of light.
Let's see. All right, let's try this one. Does the aperture of a single radio observatory have much of an impact on the quality of the image formed by the reconstitution of the Fourier components? This person says, I was wondering if several radio telescopes of the size of Arecibo would be more sensitive to the details of the image than a network of as many as 10 stations. I appreciate that the angular resolution depends on the magnitude of the baseline, but does the actual sensitivity make a difference as well?
Oh, very interesting. So it turns out that we're always battling the fact that to make a large dish and a smooth dish, both of those is very difficult. And the shorter the wavelength at which you observe, the smoother the dish has to be. So typically we're using smaller dishes that are fine-tuned to operate in the millimeter or sub-millimeter wavelengths. And typically you want the surface of the dish to be about 1/20th of a wavelength smooth, which puts a real constraint on a large telescope. So the largest telescopes we use maybe are 50 meters. Arecibo, being 300 meters across, is confined only to the lowest of frequencies, so we can't use that particular dish for EHT work. Now, if we went to space, of course, one might consider building very, very large apertures. And the way this comes into the Fourier components is that when you have a small dish, the signal-to-noise ratio in your measurement of that Fourier component can be low. So sometimes you have to integrate for longer if you have smaller dishes to get the same signal-to-noise ratio that you need with a larger dish, and the signal-to-noise ratio you need to get high-fidelity images.
Interesting. Oh, okay, here's an interesting one. Can the motion of the Earth around the sun be somehow used to increase the baseline?
Oh, that's a very interesting question. So sometimes people will ask, can you take data one day and wait for the Earth to move, and then take data another day and then combine that data somehow? So it turns out that these interferometers only work when you can take simultaneous data. So you need to sample the same plane wave as it hits different points on the Earth. So if you waited until the Earth moved significantly, you wouldn't be able to combine the same waves. Okay, the same plane wave would not be hitting the Earth as it was then, as it will be in a week or so. Now, what you could do is you could have a telescope on the other side of the sun, and you could record data at the same time on the Earth and at the antipodal point on the other side of the sun. And if you could combine that data somehow, if you could send those hard disks back to the Earth at some point, you could, in theory, combine those and then get a telescope as big as the orbit of the Earth, which is kind of exciting to think about, something for future generations.
Yes, who wouldn't want a 2 astronomical unit wide telescope? That sounds,
Yeah.
sounds good to me.
I see one question here that I think is interesting. It says, what is the size of the orbit of the photons relative to the Schwarzschild radius? And also, if photons are orbiting, what makes them escape orbit? So there are 3 basic orbits that we like to talk about, or 3 basic radii that we like to talk about for black holes. One is called the innermost stable circular orbit, and that's the orbit where matter can move around the black hole. Okay, anything interior to that, then nothing will stop the matter from spiraling into the event horizon. Okay, and that's because matter can never go the speed of light. Normally, you have to go faster and faster in order to produce this centrifugal force to keep you in orbit, right? So a geostationary satellite just moves at the rotation of the Earth, but a low Earth orbit satellite moves very quickly around the surface, around the Earth. So that's one orbit, the innermost stable circular orbit. The next one is the photon orbit. That's the innermost orbit where photons move around the black hole. And there you get the same effect. If the photon happens to veer just a little bit inside that photon orbit, it would have to spiral into the event horizon because it can't go any faster than the speed of light. And if it goes a little bit further out from that orbit, it would spiral out and then come to our eyes. So that's called that's an unstable orbit also. And then the last point, the point of no return, the last radius is the Schwarzschild radius. And that's where you go through there and you're causally distinct from the rest of the universe after that.
Here's an interesting one. Can you see evidence of frame dragging, or is the black hole not rotating quickly enough to make a difference? And perhaps you can just remind viewers what frame dragging is.
Yeah, so frame dragging is this notion where the space-time around the black hole is being pulled by the black hole itself. So you get into a situation where even if you're trying to be motionless outside this black hole, the spin of the black hole pulls you along with it. Now, so it turns out that in one way that's invisible to us. The size of the shadow, it turns out, is not very dependent at all on the spin of the black hole. Okay, because and the reason for that is that as the black hole spins, everything can come closer to it. So the matter can come closer to the black hole as it emits. But the gravitational lensing becomes stronger. So you get closer to it, but it lenses out as though it is a little bit larger. And these two effects cancel each other. So you wind up with a shadow that's about the same size. But you could measure the spin. And you could do that with the motion that we hope to detect with movies. So it turns out that even though the size of that orbit is about the same, the time it takes to move around the orbit is dramatically different by about a full order of magnitude. So for example, if you were orbiting the 4 million solar mass black hole at the center of our galaxy, Sagittarius A star, it would take you half an hour to move around that black hole at the innermost stable circular orbit if it weren't spinning. If it were maximally spinning, the shadow would be the same size, but your journey would take only 4 minutes.
Wow.
So that's a huge difference. And if we can see inhomogeneities or turbulence in the flow moving around, we could time the black hole by spatially recognizing when things are moving around it. And that would be a way to measure the spin and, of course, then frame dragging.
I hope this isn't a dumb question, but if something is moving around, you said half an hour at these innermost orbits, is that so that would mean you're orbiting at relativistic speeds?
Oh, of course, yeah. Everything around the black hole is moving at, let's say, a third or half the speed of light.
Wow. Wow. All right, let's just see here. Okay, so here's one. Are you seeing light that has been Doppler shifted to 1 millimeter? Presumably this is relativistic Doppler shift, which gives you the wavelength change. Could you elucidate on that?
Yeah, so if we had a molecular line, So if we had a known frequency that was emitted close to the black hole, then we might be able to see the Doppler shift due to the gravity or due to the motion around the black hole. What we're seeing though is continuum emission. It's basically just static that's coming towards us from near the black hole. It's broadband noise. So it's very difficult to see a Doppler shift in that sense. But in fact, we are seeing Doppler shifted waves. So they started their journey at a little higher frequency than we are receiving them. Now, it turns out that at the orbit where we think that these photons are being generated, the Doppler shift is not too large. It of course becomes infinite as you get to the event horizon, but that's a very, very steep function. So it's being born slightly shorter wavelength than we see it, but not by too much.
Just skim through here for a second.
Somebody's asking, how big across is that imaged black hole? Let me see if I have a, yeah, I'm going to share my screen if you don't mind.
Of course.
I'm going to share this because this is an MIT crowd. So if you can see my screen there, this is an XKCD comic, and there can be no greater glory than to have your scientific results shown in the XKCD comic strip. And you can see here the size. So the sun, the outermost X-planet Pluto, and then Voyager, the farthest person-made object, all fit within that shadow that marks the impact parameter of the event horizon. So basically about three or four solar systems fit inside the shadow of this black hole.
Yeah, that's a terrific way of indicating the scale, the size. Let's see. Oh, okay. So somebody is asking if the image we see is from the quote front, what would it look like if we looked at it from the other side, the back? Would it just be sort of flipped around in a certain way, or?
Yeah. So what a great question. So it turns out that, as I like to say, everybody gets to see the shadow. It's a little bit like the sunset. We see a sunset, all the red photons are the ones that have made it through the sky. Of course, the blue photons have been filtered out to be someone's blue sky directly below the sun. And in the same way, everybody gets to see a ring. All the photons that we see come from behind the black hole and are lensed around to make this ring. And all the photons that started on our side get lensed around to form a ring for, an alien civilization that happens to be looking at this black hole from the other side. So no matter how you look at it, you always see a ring. Now, the shape of that ring will change a little bit based on orientation. So if you were looking at it edge on, you might see a much more pronounced Doppler shift. So it would look more like a crescent. So that would change the shape. But if you're looking down in the same direction as the jet's coming towards you, then you would see this largely circular ring.
Some more things here. You mentioned that you want to make movies of black holes, which certainly sounds very cool. But what new information will they yield? What will we learn about black holes from these movies that we couldn't have learned from still photos?
Yeah, that's a great question. You don't want to make a movie just to make a movie, unless you're in Hollywood, of course. But this goes back to something I said earlier. If you take a still image, you can't really tell what the spin of the black hole is. But if you take a movie, then you can measure the speed at which the flow is orbiting the black hole. And now that we know the mass of the black hole, we can measure the period. And that period is a very sensitive indicator of spin. So if we can make movies of black holes, then that would be a much better way to take the measurement of spin of a black hole. And once we have the spin and the mass and the shadow size, then we can begin to test Einstein's theory in other ways, looking for violations of the no-hair theorem, for example, through looking at the quadrupole moment of the black hole and seeing if seeing if the spin and the mass combine to give you the quadrupole.
Here's an interesting question that is not about astrophysics, but it's still very relevant and timely. What effect has the current pandemic had on you and your colleagues? And I mean, I guess if everybody's working from home, certainly there have been news reports that some observatories have basically had to shut down, that they're no longer collecting data because of
Yeah.
the pandemic.
So first of all, let me say that you know, the DHT team is doing well. We are working from home. We miss our labs for those of us who do instrument work, but we're all largely able to continue on the data analysis. So we're thankful for that, and we understand that many people, of course, are undergoing hardships. So we view ourselves as being extremely fortunate to continue to work on this and tell the story and bring it to the public. But we did have to cancel our yearly observations. Every year we focus on 1-2 week period right at the change of the seasons, so that telescopes in the southern hemisphere and northern hemisphere can kind of get good weather together. And that typically happens in March and April. And after a year of preparation, we were forced to cancel those observations. So it was a real heartbreaking moment, one that we had to, of course, do because of the health of everyone is paramount, and the health of our loved ones and all of our families, which are long suffering in this effort as well, I might add. And but we're hoping to come back next year and keep it up. But what gives me hope is that this group that we've assembled, this team, is very resilient, and we've had this great success. And so we're always looking forward to the future to see how we can continue the work. And everyone is, I think, drawing strength from each other, and it's a wonderful group to work with.
I noticed we're at about the 1 hour mark, but if you're okay with, I mean, if you have a few more minutes, we'll dig up a couple more questions. Is that okay? Or
I have a few more minutes. Sure.
yeah, okay. So we'll just pull up a couple more here. Let's see. Okay, let's try this one. How much is the light near the edge of the hole Doppler shifted? Is it by a factor of 10? Question mark. It may make sense to try to look at the edge through X-rays and gamma rays if it cuts through the gas.
Yeah, so the Doppler shift at the closest points around 2 that we can see. And of course it's a very steep function. So as you approach the event horizon, it gets much higher. It goes towards infinity. But the Doppler shift, the redshift is about a factor of 2. And the same thing of the same order of magnitude of the Doppler shift. So you can look at this in the X-rays, and they have done some very interesting work for stellar mass black holes and also for supermassive black holes, looking at the iron line. So the iron line emits very strongly in the X-rays, and you can see it moving around. You can see the effects of the Doppler shift as it moves around the black hole. So you see the shape of this iron line, this spectral feature, change based on the orientation and the speed of the disk of material orbiting the black hole. So that is absolutely a very interesting technique to use, and that's one way that the X-rays can see something a little bit different than the radio waves can. I can't resist. I see one person here asks, what is the best way for the MIT alumni community to support these ongoing research efforts? Well, of course, your positive vibrations are always welcome. And again, it's very special for me to be able to speak with you here as an alum myself, and having worked at MIT for many years at the observatory. But feel free to get in touch with me through Joe and others, and we'd be happy to talk with you about ways to do that. If anyone has a spare atomic clock in their attic, do let us know. We may be able to repurpose that, or a spare radio telescope. But we're always interested and thankful to hear from the alums.
Just we'll grab just 1 or 2 more here. So someone is asking, is there any hope of imaging a binary or even a merger?
Oh, what a great question. So it turns out that one of the sources that we look at that's very bright but farther away is OJ287. It's a quasar. So it's a very bright, glowing black hole, supermassive black hole. And that particular source, which we use again to calibrate our instrument, we can't resolve the event horizon, but it's so bright that we can make sure that all the instrumentation is working well using observations of that source. But that source we think is a binary. And we think that there are 2 supermassive black holes are moving around each other. And we're observing that with the EHT, and we're analyzing those data now. So it's very timely and perceptive to ask that question. And we hope that we may be able to see the effects of rotating black holes in these very high angular resolution images when we combine what we see now with later observations of OJ 287.
It's interesting. And if, that would be an interesting parallel to the LIGO work, because the LIGO work is all about collisions and things smashing into each other. So, maybe.
Yeah, so it's very interesting you say that. It turns out that LIGO would not be sensitive to these gravitational waves because these would be much lower frequency. It takes a long time for these black holes to move around. They're kind of lumbering, elephants, circulating blue whales. But there is a new instrument, I think, being contemplated called LISA, which would launch telescopes, which would launch essentially an interferometer into space. And that's large enough that that would be sensitive to these low frequency gravitational waves that come from the mergers of supermassive black holes. So that's where the EHT and gravitational wave observing may actually start to intersect more firmly.
Let's see here now. So, someone says, okay, this is interesting. This is about naked singularity. So always an interesting subject. Speaking of the maximum speed black holes can rotate at, is there any way high resolution telescopes like this can identify a naked singularity with any degree of certainty? Parentheses, should such a singularity exist? And maybe just remind people what we mean when we're talking about a naked singularity.
Yeah, so a naked singularity basically occurs when you don't have necessarily an event horizon shielding the black hole, where the cosmic censorship conjecture does not apply. And the effect here is that you can actually start circulating around these black holes faster than the speed of light. And the way to think about this is that the black hole shadow would be formed around something like this, but it would be, through my research, smaller than what we have seen. So we do feel that there are some classes of naked singularity that have been ruled out by these results, because we know the mass of M87 to such precision that we know what to expect for these various models of non-black hole or non-event horizon shielded black hole solutions, and they don't match. So there are some exotic constructs like this that we're beginning to exclude from the EHT observations. But I hasten to add, there are some exotic constructs like boson stars or other kinds of ill-defined matter, which mimic black holes closely enough that it's still hard for us to tell apart those from a black hole.
Now I saw an interesting one here. Okay, this is short but sweet. Is there a preferential orientation of black holes, jets in the universe? I think I have a hunch what the answer is going to be, but let's hear the real answer.
Oh, I don't think there's any preferential orientation to black holes and their jets in the universe. I mean, there can be biases in which ones we can most often detect. I mean, that's in astrophysics, you always have to be careful of biases because we look at the night sky, we see what's in the night sky, but for example, the example you gave, Dan, of a pulsar, we only really see a pulsar if its jets are directed towards us. Because it's a spinning neutron star, and only if that spinning beam intersects our line of sight do we see it. So there are some preferential directions, and we'd only see ones that were pointing towards us. In the same way, we might only start to see some black holes that are pointed towards us, and that with jets pointing towards us, and that might affect the distribution of sizes and shapes we would see.
So in other words, there could be a selection effect, but ultimately the way these are oriented, we believe would be random.
That's a great way to put it.
Okay, just making sure. Okay, so someone's asking what? Oh, sorry, go ahead.
Oh, I caught an interesting question. Your work has determined the diameter of the black hole. Does the black hole pulse significantly in the radial dimension? That's a great question. So it turns out that the black hole is growing all the time because it's eating, but it's eating at such a minuscule rate that the diameter of this particular black hole, M87, is really not expanding too much at all. We do see fluctuations we think, in the emission around the black hole, and that's mostly formed by the turbulence in the accretion flow. So remember, everything is being lensed around the black hole, but every once in a while you might get something bright on one side just because there's a clump of material moving around that is more dominant on one side than the other side. So you might see the black hole appear to grow and reduce in size, but that's going to be mostly due to the accretion flow lighting up the space-time, not the photon orbit determined by the space-time itself.
So a question about putting things at a Lagrange point. You mentioned that the moon would be a good location for a telescope because it's close to the Lagrange point. And basically the question they want to know, can you expand a little bit more on what a Lagrange point is?
Oh, yeah, I'm sorry.
And why it's a good place to put something.
Yeah, so there are some points around the Earth that are in stable orbits around the sun, for example, that are not at the Earth. So there's one point a little bit further from the Earth that's in the same radial direction as the Earth from the sun. And that's what's called the L2 point. And so you could put a satellite there and it would remain motionless without the need for propellant, for example. And that's about 1 million kilometers away from the Earth. And that would be a stable place to put one of these telescopes. And then you could form an interferometer between the Earth and that Lagrange point. Now, the moon itself is not on a Lagrange point. It orbits the Earth. But if you were to put a telescope on the moon, then its orientation would change with respect to telescopes on the Earth based on its motion around the Earth. So every month or so, you'd wind up getting a full sweep around. And that would help sample many more Fourier components as well. So either the moon or the L2 point would both give you extreme length baselines, granting you sub-micro arc-second resolution.
And I know a little earlier you mentioned, this idea of putting something on the, the opposite side of the Earth's orbit from where the Earth is. So two astronomical units away on the other side of the sun. But is that just, is that just sort of joking around, or have you and your colleagues have any, is there any real hope that one day something like that might be a thing?
Well, in the radio, that might actually wind up over-resolving most things that we'd ever want to see. There is a brightness temperature limit. In other words, things have to be very, very bright in order for you to see them on these long baselines. Because if you think about it, the resolution of your telescope is so small that if you have a finite size for anything, you start to exclude some of the energy that you're receiving from that source. That's what I mean by over-resolving. You can get such good resolution that you really can't see the thing that you're trying to image. Then again, there are ways in which you can use the Earth's orbit, and that's what I think LISA is going to do, the Laser Gravitational Wave Observatory. They want to put telescopes around different points around the Earth's orbit and connect them with lasers. And in that sense, you wind up getting a very, very large effective telescope.
And I think maybe we could, this is an easy, easy for me to ask. We'll see if it's easy to answer, and maybe we'll make this the one to wrap up on. But presumably you've seen the movie Interstellar from a few years ago. So the questioner is wondering, how much did they get right? And how does, the data that you guys got, how does it compare to, the models that they used? If I recall correctly, they hired Kip Thorne as a consultant on that film. And of course, he's an expert on black holes. So I don't know, at the time, the buzz was, oh, they really put a lot of work into getting the science right. So I don't know, is there
Well, so first of all, as I recall, when they fell into the black hole, there was a bookcase there. And it was, I think, the power of love that allowed him to communicate from inside the event horizon with his daughter. I can totally confirm that, right? Black holes are all about love. But beyond that, the simulation that Kip and his colleagues did was very, very accurate. Now they're looking at a different kind of black hole. They're looking at a black hole that has a kind of a thin disk orbiting around it, whereas M87 and Sagittarius A star have more of a fluffy donut around it. So it's more of a spherical kind of accretion with some enhancement around the mid bulge. But there are some black holes that are feeding so efficiently that they funnel all the accretion into a disk, a thin disk that's orbiting around. And that's what you see in interstellar. You see a thin disk with some of the back part of the disk being lensed up over the top, and the same disk from below being seen on the bottom. And that's what gives you that round feature. Now you still see that photon orbit, because the lensed photon orbit defines the inner edge of that. But you're really seeing a thin disk, a pancake disk being lensed around the black hole. The one thing that Kip told me that he knows they got wrong. I chatted with Kip at a conference at one point about this. One side should have been fainter than the other, because one side should have been Doppler boosted to you. One side should have been Doppler boosted away from you. So one side bright, one side faint. And according to Kip, he said he went to, I think Christopher Nolan was the director, and he explained this, and then the director said, look, nobody will ever stand for that in the theaters, so we have to make it symmetric. But Kip certainly knew what he was doing. But then the director took some artistic license, as I understand it.
Fair enough. And if we had more time, we could talk about the clouds made of ice that just sort of hang in the air and that sort of thing. But no, well, listen, Shep, thank you so much for this. This was terrific. And congratulations. I think we're at approximately the 1-year anniversary of that photograph, give or take. So yeah. So that's amazing. And good luck with the future endeavors. And obviously, stay healthy. And I will read the little closing remarks here that I've been provided with. So on behalf of the Alumni Association, thank you for tuning in to this faculty forum online, and thanks to Shep Doeleman for joining us today. I'm told the alumni staff will be sure to forward to him questions that we didn't have a chance to get to on air. So again, apologies if you sent in a question, we didn't get a chance to address it in real time, but we'll try to get to it after the fact. And that the broadcast will be available on the MIT Alumni Association YouTube channel within a week of today. I think, as I mentioned, you can tweet about this using the hashtag MITalum, and you can send follow-up questions or feedback to alumnilearn@mit.edu. Thank you again for watching.
Okay, and thanks everybody. It's been a real pleasure to share with my MIT colleagues. Thanks a lot.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.